Okay, so the recording has started. So in the last class, we have started our discussion of this MOSFET. MOSFET stands for metal oxide semiconductor field effect transistor, right? We have seen and discussed about this MOSFET structure, where there are two MOSFET dimensional parameters are important, actually three. One is this L. L is the length or the gate length of this MOSFET. The other one is this W. W stands for this width of this MOSFET. And the third parameter is this TOX, that is this oxide guide thickness. Right. And we have also seen there are actually four terminals of this MOSFET. One is this gate, other one is gate, source, drain, and the fourth one is the body terminal, right? But for our discussion, initial discussion, we will assume that this body is been grounded. So as source, right, for this N-channel MOSFET. Right, and the nomenclature of this terminal was now such that this with this gate we control the flow of current, right, like this gate valve, and with from this drain is the terminal through which the channel carrier will leave the device, and the source is the terminal through which the channel carrier will enter the device. Then we have also discussed about his operation, and we have also understood like the channel formation, the concept of threshold voltage, right? And also we have understood the pinch off, and we have also like discussed why the current will saturate beyond a particular point, right? So if we then plot this ID versus VDS characteristics, then those characteristics are expected to look similar like this, right? Okay. Now, so this is the characteristics, right, for an N-channel MOSFET. So where we have seen that as we are increasing this gate voltage, as we are, okay, this MOSFET equation, these are the characteristics. This is the N-channel MOSFET, also in short, it is called as NMOS. So here with increasing this gate bias, you can see this ID is basically increasing, right? And this point, the saturation point, which is like this and this for here, that is also going to this more, that is also shifting for this higher VDS value as you are increasing this VGS, right? And similarly, if you want to plot this ID, drain current versus gate to source voltage, then that characteristics would look something like this, right? So here you understand from there, here you are changing the gate voltage, you know that there is a particular voltage which is called the threshold voltage of this N-channel MOSFET. VT means V threshold, N stands for this N-channel MOSFET or NMOS, right? And so below the threshold voltage, the current is so low that it can be considered as a zero current. Then beyond VTN, current will rise and will take a form similar, something like this, right? So here there are three regions that is quite clear, okay, from this plot. This plot is called the output characteristics. This plot is called the output characteristics. And so because here this is the ID and this is the VDS, right? And this plot is called the transfer characteristics, because it is ID versus VGS. So VGS is the input side, right? Get to source voltage. This is the input, and VID is the output current. So it is output current versus input voltage. So the name is transfer current. And output characteristics, ID is the output current, VDS is the output voltage. So that's why the name is output characteristics. Right. Now here, the point where this current would saturate, right, means this point, okay. For each point, this value will change. And for a particular gate bias, this voltage or this particular voltage where the current saturates, that is termed as VDS SAT, right? VDS SAT, and that value is given by this VGS6 minus VTN. Right? So you have to substitute this threshold voltage from this gate voltage. So that will basically give you the voltage where the current saturates. Right? So similarly, you can understand that compared to this, this value is lower, VGS value is lower. So obviously the VDS sat will shift towards bit more to the this left side, right? So that's why you are seeing this shift, right? Right. So you can find the where the current saturates, okay, for a particular gate voltage, if you know the gate voltage, right? Now, based on this thing, the in this transistor, this these characteristics can be divided into three regions. Okay, so first one is this side. Okay, so I am let me just maybe highlight this region. So this is the region where you can see the characteristics are almost parallel to this VDS axis. Later on, we will also see that these characteristics will not be actually parallel to this VDS, but it will also have some slope, as we have also seen in case of BJT characteristics, right? But this region where the characteristics are almost parallel to this VDS characteristics, this particular region for this MOSFET is termed as saturation region. Remember that, huh? So this particular region is called the saturation region, right? In BJT, this was the region where it is called the saturation region, and this was called the active region. But for remember that for MOSFET, this is the saturation region. And when you have to use this MOSFET as an amplifier, then you will operate this MOSFET in the saturation region, right? So you have to operate in the saturation region when you are using it as an amplifier. Similarly, if you see now this side, right, this side, where the current is almost linearly increasing with increase in this VDS, right, that particular region is called the triode region or the non-linear region or non-saturation region. Okay, so this region is the non-saturation region, and this region is the saturation region. And you know, obviously, when this gate voltage is below threshold voltage, the current would be like almost zero. So that way you can also guess there would be like this region where the current is zero. So this would be the cutoff region, right? So three regions, cutoff, triode region or non-saturation region, and the other one is the saturation region. For amplifier, it should be in the saturation region, means in the this yellow region. And if you want to use this transistor as a switch, then it has to be operated in these two regions, triode region and cutoff region. Okay, maybe we will come to this discussion a bit later on. Right. Now, thing is that then how do you describe this MOSFET characteristics by mathematical equations? So for that, we have two equations. Okay, which are given in this way. ID equal to Kn to VGS minus VTN into VDS minus VD square. This is one equation. I will tell you when these two equations are valid or what are the criteria for which this equation you can use. Okay, the first equation, right? That means this equation. This equation is valid in this triode region. This equation is valid in the triode region. So in the triode region, what is the criteria? That V gate voltage should be higher than the threshold voltage, right? Otherwise, the transistor will never be on, right? Otherwise, it will be in the cutoff region. So in the triode region, means this region, here this VG has to be greater than the threshold voltage, obviously, when the transistor is on. The other criteria is here, see, this VDS has to be lower than this VD sat, right? Lower than this saturation drain to source voltage. VDS is lower than this VDS set. Is this part clear to you?
Sir,
Hmm.
sir, what is VT and what is VTN?
What is VTN and the other one is what?
VG.
What is VG? Okay. So VG is, if you consider this gate potential as VG, then VG is same as VGS because you have grounded the source right here. So if you have grounded the source, then gate potential is equal to the gate to source potential. So that way you can also, if you have some confusion, you can also write VGS greater than VTN, and VTN is the threshold voltage. VTN is this voltage beyond which the transistor will start conducting. Is this fine?
Okay, sir.
Okay, so this is for the triode region and this is for the saturation region. This equation. So, right, this equation is for the saturation region. So, for saturation region, the criteria would be obviously the threshold voltage VGS has to be greater than the VTN, right? The other criteria is here, this VDS, right? This VDS has to be greater than this VDS SAT, right? That's what we have discussed. So when this VDS is greater than VDS SAT, then only you will enter in the saturation region, right? So these are the two important equations, right, for this for related to this MOSFET, right? And but these are not also, these are quite easy equations, so you should learn these equations. And here two things. First one is what is Kn, that I think we have not discussed so far. So this Kn is half W by L mu n C ox, right? So C ox, okay, let us discuss it one by one. First, what is Kn? Kn is the conduction parameter. Kn is the conduction parameter, right? W by L you already know. W is the width and L is the length of the transistor. Mu n is the mobility of electron, right? Mobility we have already discussed during our discussion on semiconductor, the basic discussion on semiconductor. And the C ox is basically epsilon ox by T ox. So epsilon is the dielectric constant of oxide. So this oxide is primarily silicon dioxide so far we are using, and T ox is the oxide thickness that I think we have already mentioned it a couple of times, right? So from this you can easily understand that this in this COX expression there is no A, means no area term, right? So basically this capacitance is this COX stands for this capacitance, or better to say gate capacitance per unit area, isn't it? COX is the gate capacitance per unit area. Is this okay with you? Is this okay with you?
Sir, what is here T ox written?
Huh? TOX. TOX is the oxide thickness that we have already seen, right, today also. This thickness. This thickness is the TOX. See here, today also we have mentioned TOX.
Okay, sir.
Right. So sometimes this Kn is also written in this fashion, that this Kn is equal to this half K dash into W by L. Right. So from here it is I understood that this K dash stands for this mu n Cox. right? So this mu n and Cox is the process parameter, means this is the mobility and this is the gate capacitance per unit area. So if you are fabricating in, suppose in a batch fabrication, lots of MOSFET, then this mu n and Cox, these two parameters would be same for all the MOSFETs. Okay, so it is just a notation of this. Sometimes this is also given as K dashed, and so you should know that K dashed stands for this mu and Cox, right? So I think so far this NMOS should be clear to you, and how you can find this ID if the gate to source voltage, threshold voltage, drain to source voltage, these are given to you, and the transistor parameters or the this conduction parameter Kn, these values are given to you. Right. But now let us think about what will happen in case of this P MOSFET or P channel MOSFET. So in N channel MOSFET, the channel is made up of, remember what the name is coming from the how the whether the channel is formed by holes or electrons. In N channel, the channel was formed by electrons. That's why the name is N. So for P channel, or from the name itself, it is clear that the channel will be made up by holes, right? So as a result, so if you have an P type, like in this is actually the N channel MOSFET. I have just copied it, right? But for a P channel MOSFET, then what you have to do, everything will alter, right? This P silicon will become N silicon, right? And this N plus would become P plus, right? These things will alter from NMOS to PMOS. So that makes this P channel MOSFET. So here, how this channel will form? So to attract now holes at this interface. So what we have to do? This is the here holes are the minority carrier. So to pull the holes near to this interface, obviously you have to apply negative bias. So when you give, suppose when you keep on increase this negative bias, so first again there will be depletion, but no threshold, means current will not flow, right? Similar discussion as we have done for this N-channel MOSFET. So at a particular negative voltage of negative gate voltage, you will be able to attract holes and create a channel here. So you'll be able to create a channel here. So that particular voltage would be the threshold voltage of this P channel MOSFET. And from this discussion only, it should be clear to you that VTP, that is the threshold voltage for this P channel MOSFET, is negative, less than 0, isn't it? Right? Okay. Now, from the name itself, see, this is the source, this is the drain. And remember, how do we define source? Source is the terminal through which the channel carriers will enter, right, in the device. So, this is the hole to supply holes. So, then at the source terminal, now you have to give a positive potential, right? Then only it can supply the holes here. Then what is the drain terminal? Drain terminal is the terminal through which the channel carrier will come out. So that means here, if it is positive, then here it should be negative. Means compared to source terminal, drain terminal should be at a lower potential, so that the carriers can come out from this device. So that's how the names are like source and drain. The same terminology is also is exactly being used in case of N-channel MOSFET as well, right? So now if you compare this N-channel, okay, this N-channel, these characteristics and this N-channel equations, this is basically equations for this N-channel, right? For this NMOS or N-channel. So if you then have to write the equations for this P-channel MOSFET, then what are the things you are going to change? So let us first write what are the parameters that we have considered in this equation. Okay. Now, so here number one is VGS. So let us write this VGS. Second is VDS. So let us write VDS. Third one is VTN. Third one is VTN. So primarily these three parameters are there in these equations. So for Kn, yeah, obviously the other one is Kn. So that will also going to change for this PMOS. right? So for PMOS, this will alter, VGS will alter, and VGS will become VSG. DS will become V of SD, VTN will become VTP, and this Kn will become Kp. And remember, this is negative value here, and this is positive value here, right? Now, why these things are occurring, I think it is easy to understand, and it is the explanation is almost similar to the explanation when we have discussed the cases of this NPN bipolar junction transistor and PNP bipolar junction transistor. Then you recall, right? We have actually altered these terminologies, right? Whenever we have this V of BE for N channel for this NPN bipolar junction transistor, for PNP, we have taken it as V of EB, right? We have altered it. So the same thing we are doing it here. VGS become V of SG, VDS become V of SD, VTN will become V of TP, right? So if you have understood this part, then let me ask you a quick question and see whether you can answer it or not. So the question is like this. So consider an P-channel MOSFET. Okay, and here this Kp value is given as this 0.2 milliamps per volt square. VTP threshold voltage is minus 0.5 volt, right? And V of SG is given as 2.08 volt. Then find ID. Yeah, could you please quickly calculate the value of ID and tell me? Yes. So, folks, how should we approach? What should be the equation?
Sir, we know the equation for the NMOS, so
Right.
we can translate the factors into it.
Right. Okay. First thing is that whether the transistor is operating in saturation or in the triode region. Quickly.
Sir,
Sir,
saturation.
Saturation, right? So you can also do it to say like V of SD should be greater than this V of SD sat, right? Now that means this VG, right? Like this. Uh, Okay, I asked you whether the transistor is operating in saturation or not. Like you have answered it is in saturation. So could you please explain why it should be in saturation?
Sir, VST should be greater than minus of VTP. So that holds.
VSG should be greater than minus of VDP, but how are you calculating finding the drain potential?
Okay, sir. I just applied the first condition.
No, that is that for first condition is no stands out for like whether the transistor is on or off, isn't
Yes, sir.
it?
Yes, sir. Yes, sir.
So whether this transistor is saturation or in the triode region. So the thing is that we can't say because we do not have the full circuit here and not sufficient information is given. So let us mention that okay, the transistor is operating in the saturation region. So say that for some case, right? So what should be the equation then? Please tell me quickly.
Sir, ID equals KP
Hmm.
times VSG plus VTP whole squared.
Okay. So this becomes 0.2 kp value, right? And this VSG is 2.08. should should it be plus 0.5 or minus 0.5 here?
Minus.
Okay. Yeah. So yeah, you have almost got it this right only. Yeah. So it is then 0.5 milliamps, right? That this would be the current. Yeah. So you have understood this P channel MOSFET. Right. So during our discussion, we'll primarily focus on this N channel only, but I will encourage you to please go through the P channel as well, because that is also been included in the syllabus.
Sir,
Hmm.
sir, can you please scroll up?
Hmm.
Sir, here why you have considered minus here in the calculation part?
Which minus? This minus?
Yes, sir. Very last.
Because the threshold voltage is negative.
Sir, but in the equation it is VGS minus VTN.
No, in this more okay. So for P channel MOSFET, the equation is VSG plus VTP, where you have to put the negative sign. Okay, because you can also understand it from here. See, V of SG is the what is the negative voltage basically you are applying in this gate terminal compared to the source terminal, right? So you know that up to threshold voltage, there will be no channel, no current, right? Then as you are increasing it beyond on the threshold voltage, then only current will flow, right? So the overdrive, that would be actually the difference between this gate voltage minus the threshold voltage, right? So it will be always the difference between this voltage. Right.
Sir, can VTP be positive here at any case?
VTP, yeah, VTP actually depends, but typically for all these MOSFETs that we will be using here, we will get this VTP as negative only. Okay, but it's not impossible to make like this threshold voltage positive. It's possible. Okay.
Okay, sir.
Okay. Now regarding the circuit symbol of N-channel MOSFET. So the circuit symbol stands out for N-channel MOSFET is in this fashion. There are 2-3 ways by which you can represent. So one of the way is like this. So you see that this is the drain terminal, this is the gate terminal, and gate is isolated by an insulator from the channel. So that has been, there is some space between these, right? This basically stands for the channel. This is drain terminal, this is a source terminal, and in the source terminal only you have an arrow mark here. And this arrow mark stands for the direction of current flow. So if this is the N channel, then obviously you have applied here positive voltage and you have applied here negative voltage, so the current will flow like this. So this arrow indicates the flow of current. Arrow, flow of current. Direction of flow of current. Okay, this arrow stands for. Now, similarly, in many books, the MOSFET is also been, represented in channel MOSFET is also been represented in this fashion. That you don't have, they don't give this arrow, but they rather put the symbol like this, right? So this is the N-channel MOSFET. So here you can obviously get understand from here, like at this gate terminal, you have to apply some positive voltage to create the channel, right? This is a drain terminal. This is the made up of electrons. So that if the electrons has to come out, then obviously this drain terminal has to be positive, right? Because from the drain terminal only the channel carrier will come out. So obviously the drain terminal is positive. So that's why we have considered here positive. Drain is positive. And the source terminal has to be lower, at a lower potential compared to this drain, right? Because source is the terminal through which the channel carrier will come inside, right? So this is the simple circuit symbol for N-channel MOSFET. Similarly, if you consider the P-channel MOSFET, so P-channel MOSFET similar to this notation, right? As we have used here, the P-channel MOSFET is being represented in this way. So here again at the source terminal, you have an arrow, and this arrow again indicates the direction of current, and that is also quite easy to understand from here, because here source is a terminal through which the channel carrier is the here holes. So to supply the holes, this has to be positive and this has to be negative, right? So the source is, this is positive, this is negative. So the current direction should be like this. So again, the arrow indicates the direction of flow of current. So this is the gate terminal this way. And, if you want to compare, use this type of notation, Then for N channel, they don't give here any bubble, but for P channel, they give here this bubble. So that is if you are using this type of representation, then it is without bubble N channel, and if you given bubble, that stands for this P channel, right? And here you see they don't give any arrow, so you have to understand which terminal is source and which terminal is drain. So always remember that for N channel MOSFET, the drain terminal is at a higher potential, and for P channel MOSFET, the source terminal is at a higher potential. So that's how you can understand which terminal is source and which terminal is drain. But if you are using this type of arrow, then obviously here notations are already been given, right? These arrow signs are already being given, so you can easily easily understand which terminal is source and which terminal is drain. Now, why this is important? Because this type of symbol is mostly used because MOSFET, it's basically interchangeable. So the source and drain, if you interchange, then there is no difference in the electrical characteristics of the MOSFET. So unlike BJT, in BJT you cannot interchange the collector and emitter. But for MOSFET, you can actually interchange the source and drain terminal, right? So basically, it is a symmetric device. Right? So that way, this type of notation is quite popular. However, in your book, these notations are used in your book. Okay, in your book, these notations are used, and we will stick to these notations only for our discussions. I hope this part is clear to you. Now again, now the MOSFET, we also know the MOSFET symbols right now. Now the next part we should discuss, but now the next part that we should discuss is regarding the biasing, right? How to bias a MOSFET. So again, like as we have discussed for BJT, probably we can use the voltage division and type of biasing to bias the gate, right? Because here this is the N channel MOSFET. From the symbol itself, it is clear, right? This is NMOS, right? And for NMOS, this terminal has to be positive and obviously higher than VG. So that way, this terminal is a positive voltage, and that you can get without using an additional voltage source by dividing this VDD through this voltage divider, right? And to restrict the current, you should have an drain resistance RD, and you have a transistor, and here this terminal, source terminal, is grounded, right? And that's how the transistor has been formed, right? Now, yes. So here this terminal is formed. Now, what is the VG? VG you can easily find out by taking a voltage division. So what is VG? VG is basically R2 by R1 plus R2 into this VDD, right? That's how you can find what is this potential. Now, once you have this potential, and if this is greater than this VTN, then you can say the transistor is on. There will be some value of ID, but you don't know whether the transistor is operating in the saturation region or in the triode region. But you can do one thing: you can assume the transistor is operating in the saturation region, do the calculation, and verify the result that whether the transistor was really operating in the saturation or not, as we have done for the bipolar junction transistor, right? We have assumed initially that the transistor is operating in the active region, and using that approximation only, we have actually extracted or evaluated the values, and then later on we have cross-check it whether our initial assumption was correct or not. So we'll do the same thing here. So we will take one example as well. But before that, let me ask you a couple of things. See here. See, if you take now a voltage, means if this is VG, and if you consider this VG and write a loop node equation here, this is quite a easy node equation, right? This is basically VG, or maybe I will write it here so that the example can be done in this side. So here this VG is equal to, this is V of GS, right? Or maybe I can write it, that would be better. This is V of GS, right? So this potential is nothing but this V of GS, right? Okay. So here, now think about it that, okay, regarding the stability, maybe I will come after this example. Okay, let us say for this particular circuit, these values are given. R1 equal to 30 kilo ohm, R2 equal to 20 kilo ohm, and this this VTN, sometimes it is also written as VTHN. TH stands for the again threshold. So this notation is also generally sometimes been used. This is equal to 1 volt and Kn value is given. You have to find what is the value of ID. Okay. Can you please find it out quickly? Or if you can tell me like how to approach. Guys, quickly. What should be the first step? First step should be to find out what is the gate voltage, gate potential, right? Here, VG. So VG is basically equal to VGS, right? For this case, right? So what is the gate potential? Gate potential would be equal to R2 by R1 plus R2 into VDD, right? So if you do that, like, if you just put the values 30, 20, and this VDD, okay, I think I forgot to mention the value of VDD. VDD should be equal to here 5 volt. Okay, just put 5 volt here. That would give you that VG, gate voltage, equal to 2 volt. So this gate voltage is obviously greater than this VTN. So obviously the transistor is on. Transistor is on, right? But we do not know whether it is in saturation or in the triode region, right? So let us assume MOSFET is in saturation region, right? If we assume that, then we can write this equation Kn VGS minus VTN square, right? Just substitute the values. Kn value is given. VGS that we have extracted as 2 minus 1, that square, that will give us 0.1 milliampere. So this ID value is coming out to be equal to 0.1 milliamps, right? Okay. Now say this RD value is also given as 20 kilo ohm, then we can find what is the value of this VD, drain potential, right? So this VD is nothing but equal to VDS here, right? Because S is been grounded. So VD is equal to VDS for this particular case. So that would be equal to VDD minus ID RD. So it is 5 volt minus 0.1 milliamps into 20 kilo ohm, right? That would give here this 3 volt, right? So VDS is here this 3 volt, right? Okay. Now what is this VDS SAT? VDS SAT is equal to VGS minus VTN, right? So what is VGS? VGS is equal to 2 volt minus 1. So this is equal to 1 volt, right? Then obviously from here we can see then this VDS is 3 volt and this is greater than VDS SAT, right? So VD is greater than VDS SAT. So that means obviously the transistor is in saturation, right? So if the transistor is in saturation, then obviously our assumption is correct. Right? So if our assumption is correct, then whatever we have, the value we have extracted that for ID, that is 0.1 milliampere, 0.1 milliampere, that is also correct. Right? So this is quite a straightforward way to extract or to find what should be the value of current for this type of circuit, which is a fixed VGS biasing circuit. Right. Now let us also quickly discuss about its stability. Okay. So let us start with that. Say, or maybe, okay. See, for this, suppose this transistor, okay, this particular transistor is now replaced with another transistor. Okay. So when you replace this transistor with another transistor, maybe of the similar type, but still there may be some change in the threshold voltage, and there may be some change in the other transistor in the value of Kn. So as a result, the transistor characteristics will also be different for these two devices. Let us say that this difference is like that. For device 1, the earlier device, we are plotting here ID versus VGS, means the transfer characteristic. Say, so this is the device 1 characteristics and this is the device 2 characteristics, and it is quite clear from this figure that they have a finite difference in the threshold voltage, right? Because you can see for this threshold voltage is this, for the green one threshold voltage is this. So there is a difference in threshold voltage, and say this is the characteristic, right? And uh, when you have, when you have used this voltage Debye biasing, so you have fixed the value of gate voltage. So that way you have fixed the value of this VG, right? So VG is fixed, right? Then this current ID, like what will be the current that is flowing through this transistor ID, that will be determined by this VG only, right? So if you take a cut line, take a straight line from here. So for device 1, this ID1 would be this much, right? For device 2, ID2 would be this much, right? So you can see that if we replace this transistor with another transistor, if their characteristic varies little bit, then it will create a good amount of change in drain current. So this is the delta ID, right? So that way, this type of circuit is not very, you can say very stable in terms of this, transistor. If you are varying one transistor with another transistor, then this is not that type of stable circuit, right? However, like as we have discussed earlier, for BJT also, if you have, suppose if you introduce in the same circuit one resistor RS, right? Like in BJT, we have introduced RE. Remember, emitter resistor. So here, if you have introduced this RS, then you will see that the stability will increase quite a lot. Now, why? Let us see that. So here, um, so we have introduced this RS here, and this is VGS. So let us write a KVL like this. Okay, here. So here, this gate voltage, this equal to VGS plus ID RS, right? This is ID, this is ID. And remember, for MOSFET, IG gate current is 0, right? Because gate is separated by an insulator from the channel. So that way, gate current is 0. So no current is flowing through this, right? Now, if you consider this transistor to be as a node, then the current which is flowing through the drain terminal, that has to be same as that of this drain terminal, right? So means drain and source terminal current should be same, right? So ID should be equal to IS. So remember that for MOSFET, right? Okay. Now, if I can, just a minute. So if I can now focus on this, then you see here this VGS, this VG is equal to VGS plus IDRS, right? Okay. Now suppose what will happen, this, okay, and here VG is fixed, right? This VG is fixed by R1, the value of R1, R2 and VDD. If you are not changing these three things, then this VG is fixed, right? Okay. Now say this ID increases, right? So if ID increase, but this part is fixed, then obviously this VGS has to reduce. If for, I'm saying, so if ID increases for any reason, it may be due to the increase in temperature or due to the change in device, it may be anyway. But for to make this equation correct, this VGS should reduce. Now when this VGS of a transistor falls, its ID will also have to be reduced, right? So that way, introducing this RS is providing a negative feedback, right? So when you are introducing this RS, you are getting a negative feedback. Similar thing what we have also seen in case of the bipolar junction transistor when we have introduced an emitter resistor in the emitter terminal, right? So I hope this part is quite similar to the bipolar junction transistor and no further discussion is required. Now regarding the stability, like as we have discussed, like similar, like for this earlier case. So say now here we are also plotting this ID versus VGS characteristics, right? Then and say these two devices. We have replaced this device with another device, and they have a separate or different device characteristics, right? Then you see we are then we, due to the introduction of this RS, right? If we are taking a loop equations, means writing these equations, which is this one, then see from this equation, this gate to source voltage is not equal to this VG, right? So we have to find it out. How can you find out? We have to draw a load line again. So draw a load line, right? So this would be the load line from this equation. See this is VG and this would be one current. You can find it out, and the slope of this line would be dependent on this RS value only, the resistance value only, right? Right. So when you get this slope, then you see that when even if this transistor is replaced by now this transistor, then the change in, okay, there will be a change in small change in this V of GS, right? VGS will change, but the resultant change in ID, that would be much smaller compared to the previous case where we do not have this RS, right? You can see the change will be this much, right, compared to the previous case where we do not have this this register RS. So that way you can see this putting one source register, right, will enhance the device, DC biasing stability, right? So let us quickly do one example before we move to the next part. So here, this is the circuit. Okay, this circuit is similar to the previous one, except here, and here we can also see the value of this RS is also been there, right? So, and the values of this R1, R2, these two resistors are given. Values of RS, RD, they are also given. Threshold voltage is given, Kn value. So you almost know all the things except the value of VDD. So VDD is 10 volt. And remember this thing for diode circuit, this remember this, difference in the notation. Generally for that, bipolar junction transistor or BJT discussion, we have used VCC to denote the supply, right? And VCC and VEE, right? But here we are using the symbol or notation VDD. VDD. If you have a negative supply source at this source terminal, then it should be VSS, right? So please be careful of these are these symbols, because then typically these symbols are generally used, okay, for MOSFET circuits and BJT circuits. Right. So here again, if you have to find then ID and VDS, VDS means this voltage, right? This voltage is VDS. Then obviously first you have to know what is the value of VG, right? So what is the value of VG? That is again quite straightforward. VDD into this R2 by R1 plus R2. And if these two resistors are similar, then we can clearly see that this will be a 5 volt only, right? Similar simple voltage division. And here you can also notice the values of R1 and R2. These are pretty high, right? Okay. Then we know this VG, then probably we can use this loop to find what is the value of this VGS, right? Okay. Now, so to do that, we can write it like VG equal to VGS plus ID RS, right? So here this VGS is equal to V is 5 volt minus ID we do not know as of now, but we know the value of RS. So writing it as the value of RS as 6 minus ID, right? Whether this ID is in milliamps, right? So ID is in milliamps and this RS is in kilo ohm. So basically if you multiply, that would give us volt, right? So you have to be careful on the units as well. Then again, we have to assume assuming saturation condition, right? We have to write this ID. We can write ID equal to this Kn VGS minus VTHN square, right? So here, if we substitute it, it becomes 5 minus. Now, let's see that VGS minus this one, right? VGS minus VGS is equal to 5 minus this one. So let us write that 5. This become okay. VGS VGS is 5 minus this one. So let me use the same color, right? 5 minus ID, and the value of threshold voltage is 1, right? That 1 that gives a square. So and here it is ID, right? So you can see this is the equation where you have ID square. So basically it's a quadratic equation. So you'll get, if you simplify it, you will get a quadratic equation like this. 18 ID square minus 25 of ID plus 8, this is equal to 0, right? If you solve it, you'll get ID value is equal to 0.88 milliamps, and so we are expecting two values quadratic equation, right, to this two. Now the question is, ID cannot have two values for a same circuit. So one of the value is possible and the other one is not. So the question is first whether 0.88 milliamps this value is possible or not. Guys, can you make a comment on this? Whether ID value of 0.88 is possible or not? Any comment? Whether ID value 0.88 is possible or not?
So that will make VGS negative.
VGS or DS?
VGS. 5 minus 6
VGS.
ID.
Okay, okay, okay. That way also you can say, right? That way also you can say. See, this, if you are considering this one, then this is how much? This is ID. ID is 0.88 and RS is how much? 6, right? So multiply it. Okay, 0.88 into 6. So that makes 5.28 volt. So if this value is 0.88, so the voltage drop here has to be 5.28. But here the VG itself is 5 volt, right? So obviously this value is not possible, right? So the correct value would be 0.5 uh, milliamps. So this would be the correct value, right? So now you know what is the value of ID, right? Now it is not ID is we know. Now to find what is VDS, that is also quite straightforward. VDS would be equal to, from this from this loop only you can write, it should be equal to minus VDD minus ID into RD plus RS, right? Take this loop, take a loop like this, right? And right, and you will get this one. So from here we know almost all the thing except yeah, we know all the things except this VDS. So that way we can also find this the value of VDS. I think it would come around 4 volt. Yeah, maybe please cross check. So we are not doing it again here for the complete calculations, but please, I request you to please do a cross check of this value. So VDS is expected to be around 4 volt here. So this 4 volt, and we have done on assumption that saturation condition. So for that we have to do a cross check. So let us do that cross check. So cross check is we have to find what is the value of VD sat. So VD sat is VGS minus VTN. So VGS. So what is the value of VGS? VG. Okay. What is the value of VGS? VGS is 5 minus 6 into ID. So that is equal to 5 minus 6 into 0.5. So this is equal to 3. So it is 2 volt. So VGS equal to 2 volt. 2 volt minus threshold voltage is 1 volt. So this gives us 1 volt, right? So VD sat is 1 volt. So this is greater than VDS sat, right? So MOSFET is in saturation as assumed, right? So our assumption is correct. So the MOSFET is in the saturation region. Is this part clear to you? It's quite straightforward, right? Just do this, solve couple of KVL. That's all. Now quickly, probably I can also do this. Now this is an interesting thing. See, the biasing using drain to gate feedback resistor. So here what we are doing, here we have this VDD, we have RD from this drain to gate. See, from this drain we have taken this resistor and we have connected to the gate terminal here. See, what would be the beauty of this if you are doing it like this? So let us write this equation. What is VGS? Okay, for this. So this is VGS, right? Okay. What is the value of IG? What is the value of IG for a MOSFET? Gate current?
0.
0.
0.
Then what would be the drop? Then what would be the drop across this RG?
0.
0. So that means this potential means this is at the same potential as of gate. If this is VG, right, then this would be also VG, isn't it? Because it's a 0 gate potential, means 0 voltage drop here, right? Okay, so we can write then VGS is basically equal to VDS. This is the drain terminal, right? So VGS is equal to VDS, right? For this type of case. So VGS is equal to VDS, okay? And what is VDS sat? VDS sat is VGS minus VTH, right? So that means, and also it is quite clear then that for this type of configuration, VDS would be always greater than this VDS sat, right? Because VDS equal to VGS, right? And VD sat is equal to VGS minus threshold voltage, right? So obviously VDS is greater than VD sat. So that means in this type of case, the transistor would always be in saturation region, right? So you can close your eyes and say like the transistor is operating in the saturation region, right? Okay. Now, if you take say, if you take one KVL, say along this loop, then what you can write, VDD is equal to ID RD plus V of DS, right? So probably this equation, I can do a small change in this and write VDS is equal to VGS. So write VGS, right? So if you now consider regarding the stability part, right? If suppose for some reason ID is increasing, right? This ID is increasing, but this VDD will have to fix, right? So this VGS has to fall. Now, when this VGS will fall, in the next turn, it will reduce this ID. So that way, if you try to connect it with our previous discussion, we can also see one negative feedback is also there for this type of configuration. And for this type of negative feedback, you can always analyze it for, or you can always say the stability of this circuit would be better, right? DC biasing stability of this circuit would be better because whenever this ID is trying to increase, right, VGS will fall, and when VGS will fall, it will try to reduce this ID. So there is a negative feedback. Okay, so I think with this we'll stop here today, right? We have an example left, but that we will continue in the next class. Not next to next class, maybe. Or so in the next class we have an exam. So please do remember that. That is on the Friday, not Wednesday. Next Wednesday we have an exam, and so for that you have to please be here in this regular class, join this regular class only, and further question paper and instructions would be shared during that time only. Okay. Okay, then thank you. If you have any questions, please feel free to ask. Okay, then thank you.
Thank you, sir.